Moving on from Lua Coco, I'm still Eric Wing. In this talk, I will share my experience of embedding JavaScript engines like we would with Lua. There is no web browser involved, but since this is a Lua audience, I want to try to provide something interesting even if you'll never touch JavaScript in your life. So while looking for an angle, I noticed a recent discussion on the Lua mailing list proposing more file system functionality in the standard library. There are assumptions baked in here like that systems are homogeneous and there's little downside. So I'm going to use this talk to share my mindset as a cross-platform embedder and show you the challenges that get in my way, and ultimately why small is beautiful. So if you remember this slide, now I switch my hats to cross-platform and game engines. Disclaimer, this talk is based on things that happened several years ago. Some information may be old. Backstory. Appcelerator is a company that makes a product called Titanium. It allows you to write native iOS and Android apps in JavaScript. They start with the native platform and embed a JavaScript engine and write language bindings. Users code in JavaScript. Additionally, they made their own cross-platform API layer in JavaScript, so when you write an app in Titanium, it should work on both platforms. Because a lot of people conflate the browser and JavaScript, I reiterate, there is no web browser involved here. This is just the JavaScript engine, just like how we embed Lua. Despite defying the web status quo, Appcelerator carved out a following in the enterprise and traditional app world, but they wanted to try to get a foothold in the video game development world. This is where we come in. Funded by Appcelerator and a big giant company that I'm not sure I'm allowed to disclose, they have big round ears, we were charged to build a game engine for Titanium as a library that Appcelerator users could opt into. One of my co-founders had already created a working prototype using all the public APIs Appcelerator had created for creating third-party libraries for Titanium. The working prototype was good enough to close the deal, but this is also where the trouble begins, and this tale. Fundamentally, the problem was abstraction, and how it killed performance, and how it prevented us from doing what we needed to do. To give you an idea of the degree of the abstraction level, Appcelerator used different JavaScript engines for iOS and Android. iOS used JavaScriptCore, Android used V8, and this is considered a hidden implementation detail. Additionally, the way Appcelerator did their binding, the bridge was heavily dependent on introspection and reflection features of Objective-C and Java. On top of that, because all the implementation detail hiding and engineers just piling on more and more layers of code over time without thinking about performance, the bridge layer became really slow. And the final nail in the coffin was that it was now impossible to write a single cross-platform module in C. Instead, you were expected to write two separate modules, an Objective-C version and a Java version. For a cross-platform game engine, this is a non-starter. We needed a deep understanding of the system architecture, and while we could see that the bridge crossing is slow, we didn't have solid numbers or context on what our theoretical maximum should be, and we need measurements and context. The plan: hack and bypass Titanium's layer and talk to JavaScript and V8 directly. Measure bridge crossing performance between Titanium and Direct. For context, also measure Lua and compare because we already have a strong sense of what's possible with Lua in the real world. Our tests confirmed that the Titanium bridge was several orders too slow. Direct.js was about 2 to 3 times Lua. Lua was expected to win because it's hard to beat Lua at its own game, but overall Direct.js performance was in the ballpark and acceptable, and now we have a good mental context to what is possible and what to expect. The next step is to figure out how to build our language bindings. JavaScript does not have a standardized API for talking to C. V8 and JS Core require completely different glue code. Fortunately, SWIG saved us. At this time, there was already an experimental JS Core and V8 backend being developed. I think the culture clash is an interesting topic, but I need to skip this for time. But a consequence of culture is that we kept getting asked the question, isn't pure JavaScript fast enough? While I was skeptical, I didn't have hard evidence one way or the other. For Platino, we were adding an open source physics engine, which was written in pure C. Luckily, somebody else had already done a re-implementation of it in pure JavaScript, So this gave us a chance to compare native C versus JavaScript Core versus V8. An important detail everyone should know is that iOS disallows JIT. Also for these devices, the iPad mini has slower hardware than the Galaxy S4. This clearly plays out in the native benchmark. Native clearly won by a lot, but more controversial, V8 lost by a lot, 40x difference against native, and it also lost JavaScript Core. Now let me emphasize this. JavaScript Core with no JIT on slower hardware beat V8 with JIT on faster hardware by over 2x. So the Google V8 hype didn't live up. JIT hype didn't live up. C is faster. This subtopic may be surprising to see, but this was a major ongoing drag on development that caused numerous technical problems. I see a lack of library developers giving talks, so I'm going to bring it up. And I'll do it by sharing my tale with V8. But first talking about the Android NDK will give you the context of the problem. All Android apps must be written using the Android SDK, which is in Java. However, Google threw us a bone and lets us build dynamic libraries using C and C++ using the Android NDK. We can ship these libraries inside our app and then use Java JNI to communicate between the languages. The Android NDK is awful. John Carmack called it half-baked. People like to remind me that Carmack has rarely complained about developer environments, even ones that were notoriously famous for being bad, such as the Sega Saturn. So this is damning. But this quote got traction because every NDK developer knows this pain. The NDK is a second-class citizen on Android with poor integration. The word on the street was that Google only has 2 full-time engineers working on the NDK. This is consistent with what's seen on the NDK mailing list. Why am I getting on Google's case? Well, Android is 8 years old. They have ignored our pleas, bug reports go into the void. Public ridicule is the only tool we have left. This is one of the richest, most powerful companies in the world with complete dominance in mobile. It is shameful it is this bad. Android does not use glibc. They wrote their own standard C library for Android called Bionic. It does not care about POSIX compliance. It doesn't even care about ANSI compliance. And 8 years into Android, it is still terrible. Some of you may have seen this on YouTube. Somebody took Lua 5.2 and built it in Borland Turbo C 1.0 for MS-DOS from 1990 without modifying the source. It built and ran. What if we tried this with the Android NDK? Build failure. This is a post from a Bionic engineer. From just 2 little paragraphs, I think it gives a lot of different insights to what's wrong. I don't have time to go over all the angles, but I'll cite this. I found a bug that had been fixed upstream in like 1996, but we had some random old version of that file. I wrote a program to run a JavaScript conformance suite called test262, which goes through 11,000 plus files. I used string lcopy in a hotspot. For a hot loop that should have taken 14 milliseconds, it took 9,000 milliseconds. Files that ship with your app are inside the APK. Think of it as a zip file. Well, you can't use the standard C library file functions like fopen and fread on anything in the APK. Google makes you use a different set of functions. On top of that, they require a parameter that comes from a God object from the Java Android activity or context class. This means existing cross-platform C and C++ libraries won't work without special modification for Android. This includes the Lua IO library. How many projects really want to do this? And it's ridiculous that this problem even exists. I was trying to get the list of my 11,000 files inside a directory in the APK. Little did I know I walked right into a well-known Android performance bug. Pessimistically, this should take no more than a few seconds. 3 hours later, I gave up and killed the process. Android has a lot of wonky behavior and rules for dynamic libraries. I wish I had time to cover this in detail because a lot of things are affected by this. It is a common source of breakage and often leads to needing to specially modify cross-platform code. For example, the Lua module system is affected if you wish to preserve the same usage semantics from other platforms. LuaSocket, for example, likes to have multiple core.so files in different subdirectories. Android moves your dynamic libraries to a single place, and no subdirectories exist there. Also, Android requires the lib prefix to exist. My preferred solution is in this slide if you're interested. Since I'm bashing on Android so much, it's only fair to call out iOS for its own sins here. Third-party dynamic libraries were forbidden on iOS until recently. This results in everything being statically linked, but this will interfere with the normal Lua module usage semantics. Again, my preferred solution is described in this slide. Back to Android, the Android NDK provides 5 different C++ standard libraries you have to choose from. Choice is not a good thing here. All are incompatible with each other. Also, the C++ standard library does not guarantee a stable ABI, so every NDK upgrade potentially breaks things. If you use dynamic linking for your standard library of choice, you must bundle it with your app because Android does not ship a copy with the OS. This is in contrast to Apple, which ships one to spare you this mess. In the real world, people build library binaries and share them. People don't upgrade their NDKs all at the same time, and versions get mixed. Also, people use multiple libraries, and each library could be built with a different NDK version. So, you would expect that the final application must include a copy of all these different C++ standard library versions that all your different libraries depend on. But Android doesn't name versions differently, so files will overwrite each other. Some of your libraries will start calling into the wrong version and bad things happen. In contrast, Microsoft Visual Studio at least has the common sense to put version numbers in the file name to avoid this very problem. So we should statically link, right? This is a warning that Android has in their documentation about static linking. So it's lose-lose. Thanks for nothing, Google. In practice, I personally found static linking to be the better of the two. So back to V8 and the original tale. The public API for V8 is C++. It uses templates and classes. Titanium uses V8, thus Titanium must use C++, and now it spreads all over. Titanium dynamically links to GNU STL, its standard library of choice. This is tied to the NDK version they downloaded at the time. The Titanium build process ships their GNU STL because they know it must be bundled with your app. Platino needs the NDK for building our pure C libraries. We download the NDK from Google. Google only provides one link to the latest. Our download time was sometime later than Appcelerator's. Platino must also compile and link against both Titanium APIs and V8, so now we have a C++ dependency we didn't really expect or want, since all we originally had was pure C code. But now we have a problem because our NDK versions don't match. Our compiling and linking to Titanium and V8 need the newer standard library version, but Titanium and V8 themselves need the older. And we didn't notice or recognize this problem as it was happening. Instead, we later got weird, hard to reproduce behaviors or crashes. Traces made no sense. There weren't any obvious clues about what the problem was. So while the usage of C++ is a hard enough problem to deal with, the fact that V8's public API was C++ exasperated the problem because it now forced C++ to be used in places that would otherwise have just remained pure C. Changing gears, Appcelerator wanted to create a next-generation product to improve many areas, including those we helped identify. The idea is to create a compiler that will read your JavaScript code and detect when you're trying to call a native platform API from Cocoa or Android. The Hyperloop compiler will then automatically generate the language bindings needed to make this call work, and then build that to create a working app. This is a really cool concept, and I encourage the Lua community to consider doing something like this. Hyperloop is open source, and it just went 1.0 a few months ago. And also don't forget to check out RubyMotion, which while it predates Hyperloop, it is even more ambitious. As part of this next generation effort, it was also decided to unify around a single JavaScript engine. Different options were considered, but ultimately JavaScriptCore was chosen in large part due to the fact that it was already built in on iOS. And V8 cannot disable JIT, so it's a non-starter. But I wanted to mention Duktape, which I found really interesting. Duktape is basically a JavaScript VM designed from the ideas of Lua. Its design and bullet points will look really familiar to any Lua embedder. But it can be a hard sell to people because it's not one of the big three. I skipped the culture clash stuff, but the phrase, "nobody ever got fired for buying IBM" is relevant here. So now we need to port JavaScriptCore to Android. But this won't be easy. It is an extremely complicated code base with platform-specific code. The build system is also very complicated. The initial attempt tried to create a build system using Google JIP, because everything Google makes is great, right? It failed. Gee, what a shock. Now I got involved. There was an existing CMake build system for some other non-Apple platforms, so my route was to make that work for Android. JavaScriptCore's main dependency is ICU, the International Components for Unicode library. It is a large library written in C++ that also has a complicated build system using AutoTools. ICU pose many challenges by itself. Due to time, I can't really cover all of them, but I want to mention one about dependencies and relating back to the dynamic library stuff from earlier. Android manufacturers might use libraries themselves for their devices. ICU is a commonly used library, so if a manufacturer makes their own ICU library and uses it in their operating system, this creates a problem for developers that want to use the same library for their own app. When they call load library on ICU, Android checks to see if the library is already loaded. In this case, the OS will see that the manufacturer's libicu is already loaded. Load library will silently skip loading the second copy and return. So your library never gets loaded. Instead, your code will try to resolve against the system one. If they were the same version, things work. But most of the time, you have a different version. And furthermore, libicu typically breaks compatibility frequently. This is another example of the pitfalls of dependencies. In 2 weeks, I got JavaScriptCore running on Android. The Appcelerator team made me feel like a hero because it solved a major technical risk. The company and the people there are a class act. I can't say enough great things about them. But deep down, I felt guilty, frustrated, and angry. Lua only took me 20 minutes to get working on Android, not 2 weeks. This feels like a failure. I just wanted to mention the WinRT Windows Phone port briefly. It was nasty. We got specialists to do this port. It took about 3 to 4 months. The big takeaway, though, is that this is the cost of size and complexity. So I now realized I had a rare opportunity. I had a standalone JavaScript core separate from Titanium that I could use. Also, JavaScript Core already has ports to other operating systems, so I can go beyond just Android and iOS. And I have the ability to create bindings pretty quickly. So I was interested in seeing how much overhead language bridging costs and the performance of the VMs. Drawing on my background, I realized I could produce a benchmark comparing C versus Lua versus JavaScript fairly quickly. I could also compare the multiple operating systems. So I grabbed SDL, the ultimate cross-platform multimedia layer used by the game industry, and wrote a sprite benchmark, first in pure C, then with Lua bindings, then with JavaScript bindings. Now I could directly compare, and I decided to also compare on all the desktops and mobile. These are my results. I also tried LuaJIT for interest. I also tested a few different video cards to see where I become GPU bound. You can ignore the Windows JavaScript Core numbers. That was a bug eventually fixed in JavaScript Core for Windows. Though again, it's worth pointing out that this was a platform-specific code issue, something that would generally not happen with Lua's pure ANSI C approach. Some highlights. C is faster than LuaJIT, which is faster than JavaScript Core JIT, which is faster than Lua, which is faster than JavaScript Core with no JIT. As one might hope, if JavaScript Core has JIT enabled, then it can beat Lua, but it isn't by a whole lot. Also, it appears that both Mac and iOS disable JIT, so Linux beats Mac. Apple should be embarrassed. For LuaJIT, I used standard C bindings and not the FFI library, so I was surprised and kind of impressed at how much LuaJIT was still able to optimize. But those places where JIT is not allowed, Lua matched LuaJIT. In the end, what does this mean? Despite the large spread in numbers, JavaScript Core is still powerful enough to deliver full-blown games at a smooth 60 frames per second, even on our slowest devices. And I even tried a Raspberry Pi. This example runs smoothly on Raspberry Pi at 60 frames per second with JavaScript Core, no problems. If you want more aesthetics, remember that shaders run directly on the video card with no language bridge. Some final conclusions. I probably would have been happier with Duktape. Lua is really nice. One thing I didn't have time to go into was specific APIs, but I like Lua's Stack API. For JavaScript, I had a hard time figuring out how to control things from the native side. Everything is possible with the Lua C Stack API. I'm not sure with these other engines. Now, if we review all the problem points from this talk with respect to Lua, it is easier to reflect on how brilliant Lua's design is. It is easy to take these things for granted until they become problems. Lua is pure C, not C++. Lua has minimal dependencies, nothing like ICU. Not all C standard libraries are equal. Lua using a small surface area helps deal with that. Lua is designed for embedding and has fast bridge calls. Lua has a nice C API. Lua is easy to build, measured in minutes instead of weeks. So crude transition to what I'm working on now. On the business side, Platino was acquired by another company, and I'm not working on that anymore. However, I was left with both all this technology infrastructure, but also this frustration that has been brewing. I feel that the popular software ecosystem is too complicated and too bloated. It is too hard to understand, too hard to modify, and nobody understands performance anymore. Cross-platform development is still terrible, and I feel there's too much emphasis on creating grand unified platforms, which make it impossible to integrate any other components that aren't from that world. I want something simple, direct, and native. I'm also tired of dealing with the religious language wars. That said, I started Blur SDK. Basically, it is a thin, lightweight SDK currently focused on 2D games. It is built completely on the SDL ecosystem with customizability and modularity as tenets. I mentioned IEP in the previous talk, so you can imagine where else I might take this. And in fact, those pictures I showed are tools for Blur made using Blur's own infrastructure. I support iOS, Android, macOS, SteamOS Linux, Windows, and Raspberry Pi. And I support C, Lua, JavaScript, and Swift. I build this engine in C and SIMD intrinsics for very high performance. You can pick the language you want to use it in. Of note for this workshop, I'm using Lua 5.3. This might be the first commercial engine to use 5.3 as I embraced it when Lua transitioned from work to beta. I'm still technically in an invitation beta phase. Most things actually work pretty well, but I keep delaying things because of the constant Swift language changes. I hope to properly launch soon, but if you're interested in early access, drop me a line. Obviously, I've just shown you how everything fundamentally works, so you should be able to build this yourself, but I hope you'll try Blur anyway. Here are my final links, but I wanted to say a couple quick words. Some of you know Carlos Icaza. He was one of the 2 co-founders of the Corona SDK and a friend to the Lua community. I was his chief architect at Corona. He left Corona and formed Lanica, and I joined him as a co-founder, which is how the events of this entire talk came to be. Well, for those who don't know, Carlos passed away unexpectedly this summer. It was quite a shock, and I'm still at a loss for words on this. But reflecting on this talk, as painful as the technical challenges were, he forced me to really get out of my comfort zone on this project, and it allowed me to grow faster and better as an engineer. For example, my first day with Lanica, the company acquired a particle engine. Honestly, the performance was total crap on Android, though the real value we paid for was in a license we were granted for a third-party editor tool, which was good. Those performance problems were one of the things that set many of the events I talked about here in motion. And ironically, all these problems fostered an environment where I could finally start doing real performance programming and start embracing things like data-oriented design and SIMD. In fact, just before he passed away, I wrote a new particle engine and designer tool in Blur. Because of our history, I went overboard with the optimizations, and it is designed for CPU cache locality, plus I wrote both the SSE2 and Neon SIMD intrinsics for all the math. It's wicked fast. I was excited to show Carlos this the week before he died because I knew he'd appreciate it, but I put it off because I wanted to polish it up, and now I regret that decision. I actually have been working on a small demo tribute for Carlos, inspired by events like this one in our relationship. I was hoping I might have it ready for the workshop today, but alas, due to various events, I was unable to complete it in time. However, once I do eventually finish it, I will post an announcement on the Lua mailing list about it. It's meant to be a fun little thing. He was also kicking my butt to launch Blur already, so I hope to launch that soon, also to honor him. Thank you.